All right, friends. So the question was, how does either, what were our choices?
How does hanging
mass
and or just or
or cart mass affect the system's acceleration? So you can measure the hanging mass and the cart mass using the triple beam balance or the electronic balances, right? Depending on what it was that you were measuring. And then we need to measure the acceleration as well, right? Measure using a balance. How are we going to measure the acceleration? Okay, so displacement maybe?
Yeah.
It's just a nice little word. What else did you know? Initial velocity? And then we can use these three to find the acceleration. Do you have an equation that relates those four things? Well, yes, you do. Surprise, surprise. If you want to look at it to make sure that you feel good about it, you can find it. Bam.
Whoa.
We have. It's my favorite one. All right. So, do you feel like you have the tools necessary to do that?
Yes.
Fantastic. All right. So now we've measured all these things. We want to know how they relate. And in particular, I want to be able to graph something so that I can see what's going on. So then you're saying, well, what am I going to graph? So you could just graph hanging mass and acceleration or cart mass and acceleration, but you might not get a line. In physics, if we don't know what to do, then we just graph our independent and dependent variables and see what happens. But in physics, if we know some more pieces to the puzzle, then let's be a little more informed, okay? And let's linearize some things so we can get a line, okay? At this point right now, you guys do not need your computers open because we're going to draw some Freebody diagrams. We're going to write some F-net equations, and we're going to do some linearization. It's going to be great. Today is an awesome day. Yay for physics. All right, so you've drawn this picture, and if you haven't yet, go ahead and do that, or some semblance of that. And then we're going to go ahead and draw free body diagrams for both the hanging mass and the cart, okay? So I'm going to give you just a moment to get started on that, and then I'm going to try and catch up with you, because I don't want to be lollygagging behind. Okay, so go ahead and start drawing those free body diagrams. All the forces acting on each of those objects. Give me just a moment. I want to make sure that you are labeling things carefully. I want to make good, clear free body diagrams. All right. Jason, what was one of the forces you had acting on the hanging mass? What did you say? The tension. And which way did the tension go? Up. Awesome. I'm going to make this a little bit bigger if I can. There we go. Ah, big. All right. Oh, so you can't see how big it is. Whoa. That's the force of the string. I'm going to call these number 1 and number 2 just to make my life easier. Is that okay? You guys can do that too if you want. You don't have to. String on 1, I'm going to call that FT1. Awesome. Chris, did you have any other forces acting on the hanging mass? Force of the earth. Which way did that one pull or push? Down. And that's what kind of a force? Awesome. Okay. Quick question before we go very far. How do these two forces compare in size?
First would be Greater because it's going down.
Because it's going down. Not only is it moving down, what is it doing in the downward direction?
Accelerating.
It's accelerating. That's the part that really matters, right? So that I don't forget that, and so I can kind of keep things organized and straight, I'm going to go ahead and write down my FNet equation for object 1. So every time I'm solving these problems, if you haven't kind of gotten this pattern ingrained in you yet, first thing you're going to do is draw your free body diagram, and then you're going to write an FNet equation, right? Because the FNet equation comes directly from that free body diagram. So we've got FNet of number 1 is going to be the tension plus the force of gravity. Is it accelerating? Yes, you said it was. So we're going to say M1 times its acceleration. I'm going to make a note here that tension pulls up and gravity pulls down. What direction does that acceleration go in?
Down.
It goes down as well. So I'm just going to make a little note here that it's negative so I don't forget. Okay. And now that I've written that there, I've realized that I'm kind of in the way of my other free body diagram. So I'm going to move that. Sorry if I messed you up. I apologize. I don't like messing people up, but it happens sometimes. All right. How are we doing so far? Everybody good? All right. Skylar, did you have any forces acting on your cart yet? Gravity, which way did that one go? Down. Force of the earth on the cart, which is number 2. That's FG2. Cool. All right. I don't know. Elizabeth, what'd you have for, you have another force?
Yeah. F surface going perpendicular to the surface.
F surface going perpendicular to the surface, something like this. F surface on number 2, perpendicular to the surface. Perpendicular because it is a?
Normal force.
Indeed it is. Everybody happy so far? Any other forces acting on the cart?
Yeah, friction.
Friction? So does friction technically exist? Yes.
Oh,
But I paid a lot of money for these carts, right? I paid a lot of money for these carts. And in the catalog, it says virtually frictionless, right? So it's okay. But let me ask this question because you brought it up, and I appreciate that you did. If there was friction, and if a mechanical engineer was looking at this, yeah, there's friction, right? But as a physicist, I'm going to be like, it's pretty little. So I don't really care about it. But mechanical engineer Lucy says there is friction. What direction is it going in? To the right. How do you know?
Because it's opposing motion and the cart is going.
And the cart is going to the left. Okay, cool. So I'm going to leave it off, okay? But know that it, because I'm going to say it's pretty darn little. All right. More forces. Anything else? The tension. Which way did that one go? Going towards the left. That's the force of the string on box 2, FT2. Okay. Any other forces you want to include in there? Spencer, do you have any more forces that you'd like to include? No? Okay, cool. If we're done with forces, then we're going to write some FNet equations. Sound good? Let's do it. FNet of object 2. Now, am I going to add all 3 of those forces together?
No. Different axes.
Yes, they're on different axes. They're perpendicular to each other. And if we learned anything from our projectile motion stuff, it's that the X stuff and the Y stuff don't mess with each other, right? Keep them separated. Okay, so we got FNet 2 in the Y direction is equal to Fn plus Fg. I didn't ask you before, but how do those 2 forces compare?
They're equal.
They're not accelerating upward.
Yes, so they add up to 0 because Fnet has to be 0 because it's not accelerating. Everybody happy? Yeah, so I'm just going to write that down so we don't forget. So that's the mass of 2 times the acceleration in the Y direction, which we're saying is 0 because it's not accelerating up or down. Fantastic. Look at us. We have so much physics that we've talked about already, but we're going to keep going. Fnet for 2 in the X direction. How many forces are acting in the X direction?
1.
Just 1. So what did you say? How do you know there's going to be acceleration? Only 1 force, and 1 force can't add up to 0. Doesn't work that way. All right. Are we doing okay so far? Everybody happy? Okay, fantastic. So we've got three F-net equations. And I'm going to zoom out for here just for a minute so we can kind of look at what our question was that we started with today. So the question that we investigated yesterday was, I messed up those colors. Sorry about that, friends. The hanging mass and the cart mass, do they affect the system's acceleration? So we have acceleration over here. I see it in two different spots. How does the acceleration for cart 2 compare to the acceleration for cart 1, or for hanging mass 1? How do those accelerations compare? Do you see where I'm looking? This thing right here and this thing right here? What's that? Why do you think they're equal?
It's like the string's like not gonna like stretch out or anything, so they're always gonna be like
Okay.
so they'll accelerate the
Okay.
same. It's a system.
So does that make sense? So it is a system. The string isn't going to stretch apart. And so if we think literally about what acceleration means, it means change in velocity over time, right? If one thing is going faster than something else, that means that their distance between them is going to get bigger or smaller depending on which one is in front, which one's behind. If the string is a given fixed length and doesn't get any longer, doesn't get any shorter, then their change in velocity has to be the same. And if their change in velocity has to be the same, that means their acceleration is the same. Which means, in a non-trivial statement, that the acceleration in both of those two equations are equal. That's a big deal. How does the acceleration, or how is it dependent on the mass? Do we see mass in here? Mm-hmm. Mm-hmm. Mass 2 is right here. That's the mass of the cart. Mass 1 is right here. That's the hanging mass. Are there any other masses hiding in this system, in this situation? No, the string is massless, right? Again, my mechanical engineer friends don't agree, but as a physicist, I'm going to say it's pretty darn close. Are there any other things where there might be some mass?
Are you pointing at gravity?
I am. Because when you calculate this, what do you get? How do you calculate the force of gravity? Mass times acceleration due to gravity, right? Yeah. So that FG, I'm just going to kind of like point out to us, oh, that's interesting. This thing right here is really M1 times, oops, they got mad at me last period by doing that, A sub G. Okay. How do the tensions compare? Speak.
You got it, Shushu.
Why? Yeah, the string isn't stretching out. The string isn't shrinking. The string is just a transfer of force, right? A tension will be the same along the entire string, always and forever, okay? So this tension here has the same magnitude as this tension here. The directions are a little different, but the magnitudes are the same. I'm going to take this equation, the orange one, and this one over here, the pink one. I'm going to put them together. We're trying to figure out something about acceleration. That's the thing we want to solve for. Do we know what the tension is? Like, do you have a value? Did you measure it? Okay, so no is the answer to that question. Second question, do you care what the tension is?
No.
No, nobody asked. It doesn't matter. Thanks. If we don't know and we don't care, is it okay to get rid of it?
Yep.
Okay, so I'm going to take this FT2 and I'm going to plug it in for FT1. Right now I have two equations and two unknowns. The only one I really want to know is acceleration, so I'm just going to put it all together, okay? So I'm going to throw these two equations together. You guys come with me on this little adventure. It's going to be fun, okay? So I'm going to take this one here. I'm going to take this one here. We'll put them together. So we've got M2 times acceleration, okay? So that is FT. I'm going to say minus, because remember my FG is negative, M1 times A sub G, And that's equal to negative M1 times A. I want you to take a look at that. I want you to not trust me on it, but to do it and figure it out and make sure it makes sense for you as well. All right. M2 times A minus M1 times A sub G. That's 9.8. And by the way, it's not going to be negative 9.8. It's just going to be plain old regular 9.8. Because I already took the negative into account here. Okay. I'm claiming is equal to negative M1 times A. How do we feel about what's in that bright pink box? Feel okay? Sometimes I make silly mistakes, so I want you to double check me and make sure I haven't made any silly mistakes. It happens sometimes. You say, great, Miss Carbling, that was fun. What's the point of this whole mess? Is that what you're thinking? There you go. Thanks for humoring me. I appreciate it. Okay. Good question. We want to get this to look like y equals mx plus b. We always want it to look like y equals mx plus b, don't we? That's like our thing. Okay. Now, right now they don't look the same. Not at all. That's what your task is going to be. So, whoa, hello, that was really big. Wowzers. So let me tell you the kind of rules or pieces that you need to know. The y needs to involve your dependent variable. What was the dependent variable again? Acceleration. The x needs to involve your dependent variable, which was either M1 or M2, right? Depending on which one you did. But there are two masses. Yeah. Write yours down. Yes. And just like we always do in these problems, then the slope and the y-intercept should only involve constants. And by that I mean things that remain constant in your investigation. Okay, so the acceleration due to gravity is something that stayed constant for all of your stuff. And then either M1 or M2, whichever one was the one that you didn't change. Okay, so you've got about 10 minutes. I would like, and I don't know exactly how things are going to work out since I've got some people that are gone. I would like for you to work with your lab group, and we'll shift if we need to. I would like you to take what's in the pink box and make it look like this. Okay? It's a little bit of a task, but I think you can do it. All right? So why don't you find your lab group people and go ahead and get started.